好，okay, so let's continue our lecture from Tuesday. So in this slide, we see the equation for point source electrical field. So equation 1.62 represents the electrical field resulting from point source Q. So the distance R determines the amount of electrical field intensity, and the direction of the amount of the electrical field intensity is represented by the unit vector AR, which is pointing from the source to the observation point. So depending on the polarity of the charge, which is either positive or negative charge, if the source is a positive charge, then the electrical field will be directing away from the point charge. On the other hand, if the polarity is inverted to negative charge, then the electrical field intensity direction will pointing into the charge. So, as shown in this figure, the distribution of the electrical field of point charge can be seen as a spherical distribution. Or for a positive point charge, all the electrical field are pointing away from the source. And you notice that there are two dashed lines on the plot, which are circles. In fact, in a three-dimensional space, those circles represent sphere, and they are referred to as equal potential surfaces, 等电位面。所以等电位面是球状分布的。事实上，等电位面也就是电压，所以实线是电场，虚线就是等电位面，the equal potential surfaces. And for any point in the space, say P, and if the charge source is placed at P prime, then the electrical field can be written in a more complete fashion, that is equation 1.62. So you can see the most apparent differences is R is written as vector R over amplitude of R to the cube. 所以原本是那个 AR 乘上 R 平方分之一嘛，但因为那个 AR 可以用 R 除上 R 这个向量除上 R 的大小，所以你就把它代换成是 R 的向量除上 R 的3次方。So as you can see here, by substituting the coordinates of point P and point P prime, the complete vector of the electrical field intensity can be written in this fashion. So below is an example. If you substitute P and P prime as 311 and 1-10 respectively, you can write up the electrical field intensity vector as shown here, which is a vector in the direction of 2, 2, 1. All right, so it's just a simple numerical example. Next is an important concept about the formulation of electrical field intensity from a more complicated electrical source, from a more complicated source geometry. And because in the next two lectures of today, we will discuss, say, the electrical field of infinitely long line source of surface or a volume. So all the complicated charged bodies in complicated geometries, the fields associated with those complicated geometry can be found using a simple rule, which is referred to as the superposition law. Superposition law here. 叠加定理，叠加定理。也就是说，总体的效果可以把它看作是单一点的效果的加总。当然它有一些前提啦，我们等一下会提到。So according to the superposition law, the total field, the field of established from complicated geometry can be found by dividing the larger object into small ones and treating those small object as point source. And then the total field can be found using the Coulomb's law, using the point charge equations to find out the total field of a complicated source. So the figure to the bottom right is an example. We see at the observation point P, it experiences electrical field resulting from 4 point charges, which are Q1, Q2, Q3, and Q4. Due to the arrangements of those charged particles, you can see that each particle provides an electrical field which are directing to different directions on point P. Nevertheless, the total field can be found as the vector sum of the 4 fields. All right, so this is referred to as the superposition law. Yeah. Well, we should check the Moodle's file first. I updated the Moodle's file, but I forgot to update the file in my USB. All right, the PDF file on the on Moodle is correct, which is what? Yeah, which is pretty much as this plot, I guess. So I just make a tiny copy of this plot in the next page, so that no, it's not the case. OK， 讲错了，应该是一个比较简单的哈。那我们用嘴巴来描述好了。OK， yeah, it's like this one. OK， so that's the black image in this figure. Okay, so let's check the description on the problem. Example 1.6. Let's consider 2-point charge, Q1 and Q2. Now that Q1 is a positive charge and Q2 is a negative one. Positive Q1, the magnitude of Q1 is A pi epsilon sub 0. It looks a little bit strange, but it's kind of the author of this textbook is kind of kind, so that your solution can be much simplified by substituting this number of charge. And Q2 is minus 4 pi epsilon sub 0. So the notice sign, the negative sign tells you that this is a negative charge. And their position are minus 1, 0, 0, and 1, 0, 0. So they are located on the x-axis, on the positive and the negative x-axis. And the problem is to find the electrical field intensity at the point 0, 0, 1. So you're kind of looking at the problem on the xz plane, And so here we go. So the horizontal axis is the x-axis, the vertical one is the z-axis. And as stated in the previous page, Q1 is located here, Q2 is over here. Now that Q1 is a positive charge, and Q2 is -1. So the field experienced by the observation point, which is 001, is directing toward the top right corner, directing to this direction as the red arrow indicates. On the other hand, because the Q2 is a negative charge, so the force is pointing toward Q2. So the field experienced at 001 is directing this way, okay? So actually, the two vectors can be found using this equation. As you are aware, for your reference, I already copied this equation 1.62 something over here. So you just substitute the coordinates, and you can find the total field of the two source, which can be combined into one vector. Okay, so the numerical value of the sum of the two vectors are 1.11a, and the most important thing is the vector. That is 3ax plus az divided by square root of 10. So this is the total field experienced at this position. What next? What next? What next? After experience this field, if you are a charged particle situated in this position, you are supposed to be moved by this electric force by a distance. However, after moving a little bit, you can say that you are moving into different directions. But you are moving into a different position. Not that at the new position, the distance to Q1, the distance to Q2, and the orientation, the direction toward Q1 and Q2 all change. So the force or the field experienced at the new position shall be changed, which means that the next moment, once you move a little bit, you will experience a different force, maybe towards a different direction. So as the time progresses, the charged particles will move in this space, to different locations, experience some change in the field, in the force, and the locus, 轨迹, the locus of the charge may not be linear, may be a curve. So let's see what happens next. So we can draw a direction line. I forgot to mention one thing, that is the black arrow over here. What is the implication of this arrow? This is the sum of the two fields, E1 from Q1 and E2 from Q2. The vector sum of the two electrical field intensity is the black one, that is the total field experienced at this position. So we just add up the two vectors based on the superposition law, okay? Supposing that the two fields has no interactions, they are decoupled. 所以讲叠加定理superposition law 的成立条件在于被叠加的这些原始数据之间，它们没有耦合，它们之间是无关的，就是说，当然叠加定理 superposition law 在工程领域是普遍被应用的一个方法，常常被用到。 那至于说力跟力之间没有 coupling 没有关系，这个假设成不成立？其实不一定啊。有的时候是即便有，但只要很小的话，我们就当作没看到。所以 superposition 有的时候即便不是那么准确，但大致的效果大致的预测还是蛮有指标意义的啦那当然对于电场的分析来讲也是啦因为假如你那个带电荷量大到一定程度的时候，其实是会有问题的OK， 不过在目前来讲的话，我们用 superposition law 其实是可以解决到大部分的问题Alright, so let's see what next. A direction line is a curve such that any given point on the curve, the field is tangential to the curve. So in previous lectures, I already said that for a curvature, the direction line is defined as the tangential direction of the point on the curve, which can be in different direction at the different points. However, the tangential direction, the direction line, can be found by what operation? What can we do to find out the tangential direction? Well, you just take a differentiation of the equation of the tangential line. You just do the differentiation. It gives you the slope, give you the direction of the direction line. Okay, so for the electrical field, it's also the path followed by an infinitesimal test charge. What is the infinitesimal? What is the infinitesimal test charge? A charge that has a very small amount of charge. OK 无限小极小的无限小的带电荷体了为什么要无限小？怕去影响到原来的电场分布啦OK， 不过从工程角度来讲就是很小就好了So the electrical field refers to the direction followed by an infinitesimal test charge when released at a point on the curve. To obtain the direction line through point 001, we go by an incremental distance from point 1 along the direction of the electrical field vector at that point to reach a new point. Compute the field at the new point, then continue this process. This process may seem a little bit awkward. Awkward 什么意思？有点尴尬了但不是很有点笨拙了意思就有点笨拙，不是很聪明，但基本上很有用所以我们现在在讲的方法其实就是在工程上面利用计算机然后来去做所谓的 numerical simulation 或 numerical computation 的一个基础事实上就是简单讲的就是凯撒讲的 divide and conquer 你把一个复杂的问题切分成很多小问题，然后一一去攻克它所以在求这个电荷在电场空间里头的移动，其实也就是一点点去做它一点点根据你的电力线的方向，然后去找出它的移动的那个量，然后在新的地点上面再去找新的受力方向，然后再去移动So it's an incremental process so we move the test charge a little bit according to the force experienced by the charge and find out the new direction and the new amount of the electrical force at the new position and continue this process until we find out the end product of this process. So in this case, suppose we move an incremental distance of 0.1 meter which is in fact a little bit large. But to demonstrate this, it may be small enough to demonstrate this process. So let's just use the example. We move a distance of 0.1 meter from 0, 0, 1 according to the electrical force direction, electrical field direction specified from the previous procedure. So the total field from Q1 and Q2 at 0, 0, 1 is this, 3AX plus AZ divided by square root of 10. Then, so we move towards this direction by a distance of 0.1 meter. So the new position is 0.09501.032. So as you can see, in the x direction, it moves as much as 3 times of the variation in the z direction. Now, according to this this vector. Okay, so move 1 portion and 3 portion on the x direction, and the total of the 2 is approximately 0.1 meter. So at the new position, that is, originally we're starting from 0, 0, 1. And the total field is pointing this way. So we move along this way by 0.1 meter. And the new position is this. So the next thing is calculate the total field at the new position. As a result, the total field, we use the equation, in this equation again, we find out the total electrical field as this. Note that the new vector is about 4.8 AX plus AZ over 4.9. So as you can see graphically, the new vector, the direction of the new vector changes a little bit from the previous one. It's tilting toward the negative x direction. And then we move along this direction by an amount of 0.1 meter to this position. That is 0.19301.052. And then we calculate the field at this new position, which varies a little bit, tilting toward the minus x direction a little bit more, as you can see from this figure. So it's shown with this dashed line over here. So if we continue this process, we can end up with let's see, do we have well, so let's guess. Let's move on this way. What is the end point of this process eventually? Well, eventually it goes to Q2 because we have a positive charge, a negative charge in space, and based on your own experience, the electrical field line will always pointing from positive charge to negative charge. So it looks like something like that. Okay. So eventually it will be pointing toward Q2. And okay, so follow some discussion. In this simple procedure demonstrated in example 1.6, there is a cumulative error associated with each step. What is a cumulative error? 累积性的误差了哈。我们刚才讲过， 这一个程序看起来有点笨拙，因为你是把它切成一些小小的分段，然后重新计算方向，重新计算移动的量。但对于所有的这种微分计算来讲，只要你的那个切分的线段长度是有限大的，它多多少少会有一些误差但基本原则是什么？你切得够细，误差就越小；切得太粗，误差就大。这是大部分的 numerical muscle 会继承的一个先天的一个特性那而且这个误差其实是会累积的因为前面错，后面就会跟着错。但是怎么样去解决这个问题？切小一点啊，多算几次啊，所以只要你切得够小，那个误差就会缩小到无关紧要了所以只要你的计算机资源充足其实这些 numerical muscle 是非常 powerful 的So here's some comment. Instead of moving the test charge by 0.1 meter from the current position, and it's moved by 0.1 meter to a point C along the directions that bisect the direction of the field at point A and point B. Well, here's another method, which just taking the middle of the two values. Well, this is also a valid approach to reduce the amount of error. So, 看一下有没有 OK。好了，你们回去看一下那个 Moodle 上面的那个 slide 所以。Well, in the textbook, there are some examples. So, depending on the amount of charge, so the plot A is Q1 equals to 2Q, Q2 equals to minus Q. So, what is the plot look like? Because one is positive, the other is negative. So we see the electrical field lines will pointing toward Q2 eventually, because opposite charge attract. And here are the other example for Q and Q. On the other hand, if the two charges are of the same polarity, they repels. And Cauchy says 一山不容二虎啦所以我们会看到的状况是小的会被大的欺负So the electrical field line of Q2, which has a small value, will be pushed over by the electrical field of the larger one. And in this case, B, the difference in the magnitude are not that apparent. But if for the first example, for Q1 equals to 81 times Q2, then you see that it's just Q2 becomes, the field, electrical field built up by Q2 becomes very 非常的委屈了OK, all right. So you can check the plot in your textbook. And next. So the foregoing illustration of the computation of electrical field intensity due to two-point charge can be extended to the computation of field intensity due to continuous charge. distributions. So here next is an important application of the superposition law. That is, for a body with continuous charge distribution, the total field built up by this complicated object can also be found using superposition law. So the continuous charge distribution can be divided into three categories that are line charges, surface charges, and volume charges. The corresponding charge density are remarked as rho is charge, the amount of charge. So rho L, the subscript is L, means that this is a line charge. Surface charge and volume charge, respectively. They have different units, okay? There will be Q over meter, Q over meter square. And volume charge density will, I'm sorry, 不是 Q 啊 ，C 啦，对不起，是 C 才对，库仑哈 ，C over meter to the cube. And this slides tabulate the process of the procedure of finding electrical field from complicated geometry, which can be divided into three steps. First, you divide the continuous charge distribution into a collection of small area, and assign the corresponding amount of charge onto these small regions. So each small region has some charges. And because the region is relatively small, so they can be regarded as point charge, can be regarded as point source. And then the third step is apply the Coulomb's law, which is applicable to point charge. And then using the superposition law to find out the total field resulting from this complicated geometry. So here is our first example. That is line charge. Well, actually, it's in the shape of a loop. So in the space, say XY plane, which is horizontal, which is usually regarded as the horizontal plane. So on the XY plane, you have a circle with a radius of what? Of A, with a radius of A. So in this circle, we have a total charge of what? Of Q. Okay, so the total charge of the circular loop is Q. We want to find out the electrical field observed on the symmetric axis, on a line which located on the symmetric axis of this loop. So, which means if the circular loop is placed on the XY plane, we want to find out the total field on any point on the z-axis. Okay? So you may have a question, can we find the total field at some places else? Well, of course you can, but the problem may be a little bit more complicated because so you know that the method we introduced today is useful, but it's useful for, in general, it's useful for certain scenarios. 只有在特定状况底下它会有用。那这个所谓的特定状况，就比如说你要用到几何学的一些奇淫巧技，把它给 问题简化、简单化哈，那你会找到答案。所以这个方法有效、有用，但不一定好用，但它容易操作哈，所以我们会先讲这个方法。事实上，我们在电磁学大概到第3章的时候吧，会教新的方法啊，会教所谓的 electrical potential. We'll use after introducing the idea of electrical potential, the field built up by established by a charged object of complicated geometry can be easily found using the idea of electrical potential. However, here we will first learn a simpler method that is using the superposition law of Coulomb's law, based on Coulomb's law. All right, so go back to this problem. We see that we have a circular loop. We want to find out the fields built up on the z-axis. So what is the first step? Divide and conquer, right? So we divide the circular loop into short pieces. In this example, we divided them into a number of 2n sections. So your question is why n, not why 2n, not just n sections? Well, of course, we do everything with a purpose, right? So the reason why we choose this to be 2n is, of course, important. So as the figures marked, we have section 1, 2, 3, all the way around, and here is 2n minus 1, 2n. So here we have n and n plus 1. So it's kind of a pair. Now you have n pairs of electrical charge sources. So we have 2n pairs of electrical charges located on opposite position of the loop. And because they are short lengths, they are short sections, they can be regarded as point charge. They can be regarded as a point charge. And the electrical field is established by those small pieces of charge can be found using Coulomb's law as this, right? We have seen this equation a couple of times. So EJ, which is the electrical field established by section J, is QJ, that is the amount of charge on this piece of short section, divided by 4 pi epsilon sub 0, which means we are located in the vacuum. Rj is the distance from J section to our observation point, which is located on the z-axis to the square here, and Arj is the vector pointing from the charge to the observation point. So first, let's try to resolve some of the unknowns in this equation. First one is the amount of charge, Qj, on this J section. So one of the conditions that I didn't mention in the problem is the charge, the total charge on this circular loop is Q, and it's distributed on this loop uniformly, homogeneously, uniformly. So according to this statement, we can easily find out each piece of the short length on this circle has the amount of charge as Q over 2 pi A, right? Because you have, I'm sorry, well, it's actually Q over 2n, right? Because you have 2n sections. So each sections have Q over 2n, right? Oh. Okay. So this is the line charge. This is the total charge. This is is the low LO on the blackboard. the line charge density. So the first one is actually the line charge density. The second one, in the parentheses, is the length of the lines. So that is 2 pi a divided by 2m. So the solution is quite straightforward. It's just q over 2m. Rj is the distance from the circle to the observation point. Say the coordinate of this observation point is z. And A is the radius of the loop. So using this relationship, you can find out the distance of R is z to the square plus A to the square, the square root of z. The square root of z squared plus a squared. Okay, all right. And that's the reason why we choose the observation point on the z-axis, because the distance is the same for every sections. And next is an important point for solving this problem. We need to use geometric relationship to solve this problem. And that's the reason why we choose the number of sections as 2n, because we will pairing each two sections on opposite direction. So here is an illustration. So this is section J, where the opposite is n plus j. It's located just the opposite of it. And go back to the Coulomb's law. The electrical field built up by the charge at the J section is what? Is the black axis over here, right? And the black axis, ARJ, can be decomposed into two components. One component is projected on the z-axis, which is in align with the red arrow, okay? The other component is pointing on the xy plane, As you can imagine, is this thin red axis, okay? Now, so the black arrow here can be decomposed as thin red axis toward the horizon and the bold red axis toward upward, pointing upward. Note that the small section on the opposite of J also produce an electrical field, which is symmetrically, which has the same amount of electrical field because the amount of charge and the distance are the same. Nevertheless, and the component, this black arrow, can be decomposed into two components as well. And one is on the z-axis, and the other is of the opposite direction of this, of the horizontal components established by section J. So what is the result? The horizontal components cancels, while the vertical components remains. So for the two pair, for the two sections of this pair, the vertical components, which is aligned to the positive z direction, remains, and the other component, which lies on the xy planes, cancels. So we have only one component for the total of the two sections, which is pointing upward. And this is true for any other pair of charge sections on this loop. So as you can see, the total electrical field will be pointing to which direction? To the top. To the top. And we'll have no components on the horizontal plane. So here, let's write up the sum, the summation of m pairs. So using the Coulomb's law of each pair, that is 4 pi epsilon sub 0 rj to the square times 2qj, because you have 2 sections in each pair. The most important part is this. ARJ, that is direction from J sections to the observation point, dot AR, that is giving you the vertical direction projection. And the result is pointing to Z direction. So ARJ dot AZ provides you the projection on the Z direction, which can be replaced with cosine alpha j. So go back to the previous page. Alpha j is what? Alpha j is the angle between the line pointing from J to observation point and the z-axis. So the angle between the two arrows is alpha j. So the projection of the black arrow on the z-axis is cosine alpha j, as you see here. And cosine alpha j can be replaced with the actual geometric parameters, because we know that for the triangle that's forming the angle alpha j, the height is z, and the distance here is a. So cosine alpha j can be replaced with z to the square plus a to the square, taking square root of this and divided by z over this one. Okay, so you can actually substitute this representation as cosine alpha j. So we do this over here. So the summation of all fields projected on the z-axis can be written in this fashion. And you collective all this because the representation in all n pairs are the same, so they can be replaced with this, right? So the total field observed at the point z will be 4 pi epsilon sub 0 z to the square a to the square times 3 over 2 times qz, and pointing to the z direction. All right, and one interesting thing is, as long as observation points is on the upper half of the plane, it's pointing upward. What happens if it placed down below the horizontal plane? Well, it will pointing downward. So depending on the position of your observation point, depending on the sign of z, the force, the electrical field can be pointing either upward or downward. And the total field, the summation of the total field can also be calculated using calculus. So here we reduce this problem using the calculus, the method of calculus. So which means that you divide them into infinite number of sections. So the amount of charge of each section can be replaced with q over 2 pi a. And the small distance on the circle is replaced by a d phi, which is a very, very short distance. And the other thing, like the projection of this, the distance r to the square is actually a to the square plus z to the square, and cosine alpha can be replaced with this representation. Now that this integral is taking the integral toward parameter 5. So everything here are not pertinent to phi, or are not related to phi. So they can be put out of the integral, like here. So the integral becomes relatively simple. It just ends up with what? Pi or 2 pi. It ends up with pi, okay? So by doing the product of pi and this, you end up with 4 pi epsilon sub 0 blah blah blah, which is the same as our previous result. So it's again validate the method of superposition law. The divide and conquer method is a valid one. All right. So so the conclusion now. So the two methods shall give you the same result. Nevertheless, the first method is more appropriate or more suitable for use of for writing up the solution in terms of computer code. Okay? All right, so let's take a short break.